Hello and welcome to this Spotlight talk. My name is Mehdi Benes. I'm a professor at the University of Oulu. I'm very happy today to be giving this talk with Timothy Oshie, who is the CTO at DeepSeek in the US. So the title of our Spotlight is about connected edge intelligence for beyond 5G and 6G. So I'll be giving the first part, and then Tim will provide his second part of the talk. So traditionally, we are accustomed to centralized machine learning, in which devices generate data, say at the edge, and then communicate this raw data to the server, and then the server just trains a model using vast amount of data, the compute power, and then train a model, right? So this essentially has a number of issues in terms of violating privacy, high latency, and bandwidth inefficiency. So in 2017, Google came up with this very nice idea of federated learning, where now instead of transmitting raw and private data, devices at the network edge will be essentially transmitting their model updates, right? Which are obtained by running few, stochastic gradient descent, say, over their local data, and then use a server so as to aggregate these models over the air, and then communicate back these models until the algorithm converge. And this has a number of interesting, kind of benefits in terms of bandwidth efficiency. Obviously, it uses the cloud still, but in a different manner, and is essentially privacy preserved. Now, you can also try to get rid of the server, and this is what we collectively refer to as swarm AI or collective intelligence or other similar terms, where now essentially these devices need to train again this model in a kind of peer-to-peer manner by communicating directly over D2D or maybe some mesh topology. So this inherits the benefits of federated learning, but also scalability. Now, this recent move towards federated and fully distributed machine learning essentially gives rise to this very interesting interplay between machine learning on one hand and then wireless communication or networking on the other hand, where now we have a number of constraints. For example, now devices need to train their models under resource constraints. So this could be compute, storage, memory, bandwidth, and also this non-IEEE data distribution or statistical heterogeneity of the data, and also the fact that now we are dealing with the small data regime, right, as opposed to the centralized big data based regime. On the other hand, these devices need to learn how to communicate now under, of course, channel dynamics, right? So the channel may be, of course, changing, blocked, and so on and so forth. Communication bandwidth may be limited, and other network dynamics. So this kind of co-design between machine learning and communication essentially gives rise to very interesting now problems. For example, how do you train a model in a communication efficient, low latency, reliable, and scalable manner, right? How do you do communication efficient, fast inference, robust inference, right, over wireless, right? And how do you also do that in the case of, for example, reinforcement learning or control? Now, for this talk, I'll basically focus on kind of three type of techniques. So the first one is called model parameter exchange, where, as the name suggests, here the devices will communicate the model parameters, right? So this is essentially what federated learning does. But you could also try to do it in a kind of serverless case, meaning training a model over a graph. Then you have the model output exchange, where now the devices will communicate their model output or logits, right? So here we developed a nice technique called federated distillation. And the third one, which is essentially about this co-design, that is how to exploit the natural aggregation function essentially of the multiple access channel, right? So you have the number of devices, and then they want to communicate perhaps in one time slot to the server as opposed to orthogonal resources, right? So we will come back to this idea a bit later. So one of the first applications of federated learning in wireless essentially was in the context of ultra reliable vehicular communication. So what you have here, you have a number of vehicles, and these vehicles need to essentially, for example, minimize the transmit power to their receiver, right? And then they have to do so under the constraint of network-wide latency constraint, right? Now, this distribution essentially is not, I mean, this is a global kind of knowledge, right, that the devices don't have. So what we do here, we just run the kind of classical federated learning, where now every device, based on the data that it has, will kind of run few steps of stochastic gradient descent, right? and then communicate this to the server, and then the server just aggregates these models, right? Here we went a little bit beyond vanilla federated learning, essentially because we were interested in this tail distribution, right? Because we were again in this kind of ultra reliable communication setting, where we were actually trying to characterize the tail distribution of this distribution, which is actually well known, and it's referred to as the generalized partial distribution, which says that you only need to estimate the shape and scale of this distribution from data, right? So this is what you actually see here in this maximum likelihood estimation. So kind of very easy application of federated learning. What you can see here, essentially, this is the communication reliability of the centralized approach versus the proposed approach. This is the exchange number of kind of communication costs, and this is the total number of vehicles. So what you can see here, essentially, that we can achieve the same reliability as a centralized approach while communicating, of course, much less, right? And this, bear in mind, this is just in a traffic safety setting. So now if this was kind of a navigation, high definition maps, these gains could be even more pronounced, right? But this was, again, very interesting application of federated learning in wireless communication. Now, what we typically do now, we also try to, go from this kind of federated learning towards this kind of settings where we don't have a server anymore. So we have a graph, right? So here we were interested in this idea of training a model now over a chain topology, right? But of course, this could be generalized further to other topologies where now you have a device, right? You have two groups, two clusters, and within every cluster, you have this worker or device, which is now communicating with only two neighboring devices, as opposed to the other federated learning case where all the workers, all the devices communicate to the server, right? So this is essentially what we did, and here again we were interested in proving convergence of this algorithm compared to the kind of federated learning setting, right? And this idea was called GADMAP for group, ADMAP for alternating differential method of multipliers. Okay, so now in terms of results, you can see this is the objective error, right? This was in a linear regression task, number of iterations. So here, number of baselines. We have gradient descent. You have other ones. I mean, just keep them, as baselines. And the proposed approach here essentially is here. So as you can see, there's a significant, performance improvements here. You see, due to the fact that we leverage this kind of spatial sparsity here in the network. Whereas here, this is kind of the federated learning idea, meaning using a server, and this is a completely distributed manner. Here, what we were also interested in is in this consensus penalty row here, right, from 3 to 7, to essentially capture this non-IID distribution aspect, which gives rise to kind of a disagreement among these workers when training this model. But again, you can see that there's a significant gain compared to the server-based, and then of course not to characterize the penalty of the disagreement can also be nicely done here with this parameter. We can also go beyond this now towards instead of transmitting the full model, right, full precision model of from the devices to others, we can look at this idea of model quantization, and this is very kind of prevalent in the literature. So now what would be the performance when you now quantize a model, say to 1 bit, 2 bit, right? Does the algorithm converge, first of all? And is there a drop in terms of accuracy, right? Can I get a free meal, meaning that I can maintain the same accuracy while transmitting much less? That's essentially what we looked at here in this setting. This is the loss function, test loss. This is the total number of transmitted bits. This is the full precision one, right? This is the gradient descent. So you can see here essentially, I mean, again, the performance gain here, when you quantize the model here, without achieving any, accuracy loss. So again, this is kind of very interesting point to note. Now, for this wireless machine learning co-design, essentially, we were interested in comparing two type of kind of approaches. So the digital federated learning, where now every device is assigned orthogonal resource, right, when it communicates to the server, versus the analog federated learning, where now we leverage essentially this superposition of all these modulated updates of the workers, right, on the uplink, and comparing essentially the performance in terms of conversions and also in terms of kind of communication efficiency and also energy efficiency. So just bear in mind that here essentially we are flipping a bit the paradigm, because once you go from here to here, what you're saying is that I'm actually harnessing the interference, right, as opposed to orthogonal allocation here. But you can also get sometimes privacy for free because the channel is acting as a kind of natural aggregator, right? So when you actually, compare these two approaches, this is the digital approach, right? This is the analog approach for test accuracy versus the number of communication uploads or rounds. You see immediately that the digital approach really struggles before it can actually start to match the performance of the analog baseline. We even try to be kind to it by giving it, say, 10 times more resources, but still it was really struggling to come up, on par with the analog. So this is a very, very nice idea where now you could, use it, for example, perhaps in a controlled environment, maybe in a factory, right, where all these sensors are kind of collocated, right? So instead of just doing orthogonal allocation, maybe just let it, leverage this idea of analog over the air aggregation. In terms of energy efficiency, also things are very interesting because you can see here, this is a signal to noise ratio, this is a test accuracy, the analog baseline is here, and you can see actually that you need to, reach perhaps here 15 dB, and then the performance of the digital federated learning start to really, improve, right? But, however, note that the analog approach is always pretty good, right? Even if you double the number of, channel users, you can see the performance is still the same, right? Very good. Now, moving on to a different type of technique, which is actually very interested, say, when the uplink channel is kind of bottleneck. So we call this federated distillation, which comes from knowledge distillation or a teacher-student model. So here what you have a number of devices, again, same setting as before, and now these devices are communicating the logit, right, or their model output of their neural network. Then the server will aggregate this kind of logits here, and then it will try to distill this knowledge acquired from other, say, devices towards a student. So this is your student here, right? Now what you actually just do essentially is write down, this is the model updates, so the equation of your model updates, this is the weight, right? So at time k or epoch k, this is the learning rate, this is the gradient of the loss. Typically you don't have this term, but now with this idea of federated distillation, you're actually adding this regularization term here, which quantifies the difference between the prediction of the teacher and then the student. So say if this prediction error is very large, then you would add this as a kind of teaching signal to update your model in a right way. Okay, so now, if you want to see the performance, this is the sum communication cost, right? This is the number of devices. This is federated learning. This is federated distillation. You can see there's a huge gain in terms of communication efficiency, right? When you compare these two approaches, simply because, again, here we communicate the entire models, and here we communicate the model output, right? Now there's a little bump in terms of performance. So this is the test accuracy. You can see we are a little bit less here, right, in terms of accuracy, which gives rise again to this very interesting trade-off between communication on one hand and then test accuracy on the other hand. But you could still bridge these two gaps, and actually we did it in follow-up works. Now, for what's coming next, we think this may be essentially sitting at the intersection of two revolutions, namely communication on one hand and machine learning. So let's take a look. Let's start with machine learning. So first of all, we need to essentially discuss the fact that now, of course, when training our model, we typically obsessed or focused mainly on test accuracy maximization, right? So now we see, of course, some efforts in terms of taking into account energy bill of training a model, which is very important for sustainability. But the most importantly, perhaps, is the fact that current models actually are very brittle, right? They are not robust. They do not generalize across multiple environments, right? Also, the fact that federated learning, despite the kind of big hype, this essentially is still a function approximating, right? It still does just curve fitting, it just interpolates, right? It doesn't actually learn any kind of knowledge, right? So now, of course, what we need to now bring in as a new kind of ingredient is reasoning, right? We need to be able to now bring in kind of some novel representations that allow us to do reasoning, extrapolation, imagination. So that's essentially what actually we propose. So there are these 6 desiderata that should actually serve us to really go after this kind of 2 cognitive tasks. So first of all, of course, we need to learn representations which are function of the data. Obviously, they have to be minimal, sufficient, but these 2 actually have already been used. Now, the new ones essentially are referred to as invariants. So here we need to learn invariant representations, robust representation which has structure, maybe symmetries, maybe they are invariant to noise, occlusion, shifts, so on and so forth. They also have to be disentangled. This is very important in order to compose, for example, new representations, right? And of course, causality, since of course just relying on statistical correlations is really not the right way to do it. And then finally, emergence. Emergence is a very important aspect, for example, in the context of even communication. Now, the objective now becomes the following. So now we need to learn semantic representations, right? Satisfying these 6 desiderata, or at least few of these, three kind of four desiderata, in order to, for example, now either train a model, maybe use it for inference tasks, control tasks, right? And if we manage to do this, essentially we'll be improving our sample complexity, so transmitting less data will be even more reliable, more robust, perhaps even more energy efficient, right? So there are a lot of interesting benefits that are still not, achieved today. The second revolution, without a surprise, comes from the communication discipline, or what people refer to as the post-channel, right, or semantic communication. So really here what we're talking about here is going back to the 1948 paper of Claude Shannon, which laid out these 3 levels of definition of communication. Level A being how to accurately transmit symbols from a point A to point B, right? So here essentially, this is essentially also where all our current 6G KPIs are coming from. But here the question that begs itself is whether this is the right type of communication that we need to pursue once we talk about human-machine interaction, machine-to-machine interaction. Is really the goal is to transmit X and or produce X hat? Is it really how humans' brains operate? Probably not, right? So it turns out that even in his paper, 1948, there were 2 levels which are referred to as a semantic and effectiveness level. So here the idea essentially is that now instead of treating communication as a reconstruction task, what we are trying to do here is to essentially emerge some sort of communication between 2 agents through sensing, actuating within a given shared environment. And of course, this is where machine learning now comes to play a big role, because essentially now we need to do this from data, right? So how do you learn this semantic representations, while interacting with other agents, while interacting with the environment? This is something that we have not done yet, right? And this will allow us now to then, incorporate, for example, reasoning, right? So causal reasoning, perhaps counterfactual reasoning, and just, other kind of cognitive tasks that will unleash essentially 6G or perhaps even beyond, right? So the interplay between semantic communication and system to machine learning gives rise to this very interesting vision. We call it Vision X, where now from a machine learning perspective, the idea is to move away from learning in data space. It could be an image, pixel, could be any other observational data, towards learning semantic representations of the real world, right? So in terms of object relations, agent relations, and so on. And now, from a communication perspective, we'd like, of course, to move away from this kind of idea of just reconstruction tasks, right, or how to best encode data, as in the Shannonian information case, towards really inducing behavioral change through interactions among agents in the environment, right, and using these high-level semantic representations to essentially communicate in a much more efficient manner, right? Instead of just reconstructing the task, which is really what Shannon communication does. And with this, of course, we have many benefits in terms of less data or high sample complexity, more reliability, more energy efficiency, and truly intelligent. And with this, thank you very much. Now Tim will present his second part. Thank you.